simple computation whose result is just 1 over st, where s and t are the usual nanosecond variables. Up to a sign. Yeah, an important sign, which I'm not. So now what we need to do is take the residue on the left-hand side. And the analysis is very simple, similar to, yes?
T is K2 plus K3.
Oh, sorry, thank you, thank you. On the left-hand side, if we take the residue of the sum of Feynman diagrams, first of all, there's going to be the same overall factor. And once again, the reason is because the only Feynman diagrams in this sum that contribute to the residue are those which have all 4 of these propagators. And since they have all 4 of these propagators, we're going to get this same rational factor pulled out of the entire sum of contributing Feynman diagrams. And then you can just compute the residue of that, which gives the same ST factor, times a product of 4 tree amplitudes. So this quantity represents the product of 4 tree amplitudes. Now, it's a very simple calculation to evaluate that product explicitly using the expressions for the now here is the first time where I'm really specifying theory. So these are going to be tree-level scattering amplitudes for gluons. So the 3-point amplitude with 2 positive and 1 negative helicity gluons given by that formula. And then we have its parity conjugate. Now, in order to do this sum, let me go ahead and for definiteness, let's pick a helicity assignment. Let's choose 1 and 2 to be negative helicity gluons and 3 and 4 to be positive helicity gluons. Then there are 2 possible kinds of contributions here. Let's go ahead and draw them all out. Here I have 1 minus, 2 minus, 3 plus, 4 plus. 1 minus, 2 minus, 3 plus, 4 plus. And the 2 contributions differ by the helicities of the exchanged gluons. So of course, in our sum over Feynman diagrams, there are going to be contributions from every possible particle that's allowed to propagate in that loop. So in this case, we have a sum over these 2 kinds of Feynman diagrams. Now, of course, we have to evaluate this. This is to be evaluated at the location or at the singularities. let's do the two calculations separately. First, let's evaluate this product of tree amplitudes at the point in loop momentum space given by L1, where L1 is the expression over there. Well, this diagram here, okay, it's a product of 4 tree amplitudes. The first contributing part is this tree amplitude, which, if we use this expression here for the 3-particle MHV amplitude, this is equal to 1 comma L cubed. So I'm going to label the momentum here by L, obviously. The momentum here is L minus K1. The momentum here is L minus K1 minus K2. Here it's L plus K4. So continuing the calculation here, it's 1 comma L, and then 1 comma L minus K1, and then L minus K1 comma L. Now, I'm using a slightly abusive notation here, but it does make sense. Normally, if L were just a completely random momentum, this symbol here wouldn't make any sense. Because what do I mean by the lambda component, the lambda spinor helicity component of a random L? Fortunately, this does make sense because, of course, I'm evaluating this at a point where that's actually null. And this is also null. So all of these symbols here do make sense. Now, the part that I've written here is just the tree amplitude corresponding to that corner. Of course, I then have to take a product where I multiply it by 3 other tree amplitudes. But fortunately, I can stop here because unless I've made a mistake, if we look at our formula for L1, it's proportional to the spinor helicity variable lambda 1. So this numerator factor gives us a 0. Okay, so let me try to make a chart here. There's not much room left. So I have these 2 possible contributing diagrams. And I found that at the singularity L1, this diagram contributes 0. You'll be unsurprised to learn that at the other singularity, the other diagram contributes 0 for essentially the same reason, or the parity conjugate of that reason, essentially. And then I won't bore you with the details of the calculation, but if you go ahead and compute the product of the 4 tree amplitudes, you find that it simplifies quite dramatically. And the 2 contributions turn out to be identical. So in both cases, okay, so to summarize, what we learned is that both sides of that equation on the far left board have 2 of what we call maximal cuts. A maximal cut is one where you cut all of the propagators that are visible. And in this diagram, there are 4 propagators. If you cut all 4 of them, then in this case, you've isolated your singularity at localized points in loop momentum space. There are 2 such singularities, and we found that at both singularities, the residue of the left-hand side, the residue of the sum of Feynman diagrams is the same. It happens to give the same answer in an interesting way. At this point, it's 0 plus this expression, whereas at the parity conjugate point, it's that expression plus 0. But in both cases, they give the same answer. So the conclusion is that the sum of the one-loop Feynman diagrams contributing to this process is ST times this quantity times this scalar integral. And now I should be honest and say, I mean, let's be clear about what we've done here. We've now checked that the rational function given by this sum of Feynman diagrams and this rational function have the same residues on all maximal cuts, so on all singularities where all four propagators are simultaneously zero. So to be honest here, I can't yet conclude necessarily that these are identical as rational functions. I have to add the caveat that this is possibly plus additional terms with residue 0 at L equals L1 and L equals L2. Now, if you're in a completely general quantum field theory, it can be really quite difficult, in the absence of a better argument, to convince yourself whether or not there are additional terms in this form. Now, at one loop, you can appeal to the fact that bases of scalar integrals are known, so you can expand any Feynman diagram in terms of box integrals, triangle integrals, bubble integrals. At higher loop, it's still quite a mess. So the generalized unitarity method relies on your being able to have some argument, possibly by checking some leading singularities. Okay, here I only looked at singularities that were pointwise in loop momentum space. You could relax one of the conditions, and you could look at a triple cut of both sides of the equation, or a double cut. So you need a lot more machinery to be able to conclude that this is actually a correct statement as it stands. But fortunately, in the most beautiful case, the case of n equals 4 super 8 mils, indeed, there are no additional contributions. But in less supersymmetric theories, there certainly would be additional terms, which you have to probe via other means.
Excuse me, Marcus? Is it completely obvious that you get the same contribution when the rest of the n equal 4 spectrum is running?
Well, in this case, in this particular case, nothing else can run. Because if you think about it, this is a super field. Here you've saturated the Grassmann variables. You can't let anything else run in this. There is no amplitude for like, in other words, what I'm trying to say. Yeah. Normally, of course, you do have to write. Normally, the best way to include the sum over the full supermultiplet is not to write a plus sign, but to write an integral over the Grassmann parameter of the particle going around the loop. But in this particular case, these are the only two contributions.
Is there a factor of 2 if you sum over 2 residues?
No, because here I'm summing over both residues, and I get 0 plus this, and there I get 0 plus that. I mean, that plus 0. Yeah. So the factor of 2 will come in the next example. Now I want to try to recycle as much as possible of this. Suppose we look at a 5-particle amplitude. Oops. And why did no one complain that my labels weren't cyclic? Oh, they were cyclic. Okay, good. You reversed your cyclic. Yeah,
You were
reverse psychology. I'm driving myself crazy. Yeah. Okay.
I never liked the first one.
Yeah.
It really hurt my head when you did it that way. Too early in the morning.
Yeah. It's dinner time. Perfect time for giving a lecture. Let's look at the corresponding 5-particle amplitude, and I'll try to recycle as much of the board as possible. Let's guess that let's guess that our answer will be expressed in terms of this simple scalar box integral. The only slight modification I need to do is put a plus k5 on the square. We'll see that this turns out to be, we'll see that this ansatz will turn out not to work for a very interesting reason. Great, I'm able to recycle quite a bit of this. That's fantastic. The only thing that changes a little bit is the explicit formula for the location of the singularities. So once again, you look at this thing as a rational function of L, and you ask, where in loop momentum space does this have isolated singularities? Or leading singularities? We should have used that phrase before. So there are 2 such singularities, and we call them leading singularities. Because they're the ones of maximal codimension in loop momentum space. In this case, they're point-like in loop momentum space. So the only thing that changes is the explicit expression, which now looks like this. And of course, the parity confidence. I'll just delete this board and leave it as an exercise for you to check that at this point, all 4 of those propagators vanish. And this turns out to be exactly the same. So I'm going to leave that. Very efficient today. The only thing that changes is over here when we come to the product of the 4 tree amplitudes. So,
Sorry, do you still want to call it TNS? It's not going to be confusing.
they're still given by this formula. Is there a problem? Okay, how about this?
Now you put different actually same.
Yeah. Okay, let me call this k1 plus k2 squared times k2 plus k3 squared. Or even better, let me just call them S12, S23, where Sij is defined as ki plus kj. Okay, this all goes through. This is going to get a little messier, so let me delete this and let me make a comment about the factor of 2, because, well, I'll wait. The factor of 2 is there if you don't view these as contour intervals, but if you view them as delta functions. But the better time to make that comment is right after we finish this guy. Once again, there are 2 possible contributions. One minus, 2 minus, 3 plus, 3 plus. minus 2 minus 3 plus 4 plus 5 plus. So let's try first the helicity configuration where this is plus, and that's also plus, and that's minus, so that's plus, so that's minus, so that's minus here. Here you have to be able to exchange either one in that diagram. Versus over here, if I try to have this one be negative, then here, this whole diagram is immediately equal to 0. I mean, maybe you should have said that I shouldn't have bothered drawing it in the first place, but I just want to call your attention to the fact that there's no valid helicity assignment here because you've got a 4-point amplitude with 3 positive helicity gluons. This corner vanishes. So this is not a contributing helicity assignment. And similarly, okay, the point I'm trying to make is that if you remember in the previous case, which I deleted, what happened was that at one of the 2 leading singularities, well, we found that this amplitude was an MHV amplitude, and therefore it gave 0 when evaluated on the locus L1. And on the other leading singularity, this was an anti-MHV or MHV bar amplitude, which vanished on the locus on the leading singularity Q2. What happens in this case is that there is no valid helicity assignment when this lower left-hand corner is an MHV amplitude. It can only be MHV bar. So at the singularity L1, this evaluates, and this is a little bit of algebra, but I skipped it last time, so I'm definitely going to skip it this time. But at the singularity L2, it evaluates to 0. So this is very different from the 4-particle case. In the 4-particle case, we saw that there were 2 leading singularities. And at each one, the residue was given by the same expression. It was something plus 0 or 0 plus something for the same something. In this case, what we found is that there are 2 leading singularities. Well, we thought there might be 2 leading singularities, but at one of them, the residue is actually 0. So if you have a pole whose residue is 0, what that's really telling you is that there's no pole at all. So going back to this ansatz, or this guess, we found that it can't possibly be correct, because this rational function here definitely has singularities at both L1 and L2. The residue is the same in both singularities. But the sum over Feynman diagrams only has a residue at L1, not at L2. So there's no possible choice of C which can render this equation correct at the level of rational functions. So I won't go through all the details, but the resolution is that the integrand should be represented as C1 times this scalar Feynman diagram plus sigma plus another coefficient times the pentagon. so now, I won't go through the math, but the idea is compute the residues of both sides at L equals L1 and at L equals L2. That gives you two linear equations for your two coefficients. Which you can solve. There's a little bit of more of a miracle there because I pretended, we've only looked at rational functions, we've only looked at leading singularities corresponding to this diagram. But of course I've got a plus cyclic here. Each term in that plus cyclic expansion has its own pair of leading singularities. So the right way to think about this is that this whole thing, viewed as a rational function, actually has 10 different points in complex L space where there's a pole on both sides. So it turns out to be true that you can determine these two coefficients C1 and C2 just by looking, for example, at these two poles. So it's a consistency check on the solution that the same solution works at any of the other 8 singularities. But I just thought it was important to mention that. Now, are there any questions so far?
Just comment about the issue of the factor of 2.
Yeah.
I mean, there's never a factor of 2 to begin with, because you're looking at the leading singularity at one place and at another place, and you don't have a choice to add or subtract, or they just have to work at every place individually. It's just that there they happen to be, the 4 points happen to be equal up the side, but yeah, they happen to be equal, and here they don't.
So yeah, I did want to say more about that. So when we actually compute the loop amplitude, what we're instructed to do is to integrate this quantity, or this quantity, along a contour where L runs, each of the 4 components of L runs over the real axis from minus infinity to plus infinity with a particular and important I epsilon prescription. Essentially what we're doing here is we're saying, okay, if we want this and this to be equal as rational functions, we should be able to integrate the left-hand side and the right-hand side over any contour, and they should give the same answer. So let's choose a contour that circles, in the sense of taking a Cauchy residue, and it circles the leading singularities on both sides. The factor of 2 that you're thinking about came from a way of thinking about this process where instead of thinking about this as a contour integral, you replace each of these 4 propagators by a delta function. Okay? And then the logic was that, when you have an integral of a delta function, you're instructed to sum over the different solutions of the delta function. But the problem here, that in a sense that doesn't make complete sense because these loop moments are complex. They live off in the complex plane. They're not real valued, even for real valued momentum, K1, K2, K3, K4. So it doesn't really make sense that you would integrate over the real L axis, even with some delta function. I'm just trying to say it's not particularly well defined. A more well defined operation